Welcome back, math enthusiasts. I'm Carlo, and in this video, we will explore the concept of definite integrals and their properties. We will also illustrate definite integral using the fundamental theorem of calculus. A definite integral computes the area between a curve and the x-axis over a given interval. It is a fundamental concept in calculus built upon the definite integral, which is the antiderivative of a function. The definite integral provides a single numerical value representing the signed area between the curve and the x-axis, taking into account both positive and negative contributions. The definite integral of a function f of x over the interval a and b is defined as the difference between the values of its antiderivative at points a and b. Mathematically, it is represented as the definite integral of f of x from a to b is equal to f of b minus f of a, where f of x is an antiderivative of f of x. The definite integral provides a numerical value that represents the signed area between the curve and the x-axis over the interval a and b. These are several important properties of definite integral that make them versatile and useful in various applications. So the first property is the definite integral of f of x from a to b is equal to the negative definite integral of f of x from b to a. We can interchange the limits on any definite integral. All that we need to do is stack a minus signs onto the integral when we do. So the next property is the definite integral of f of x from a to a is just equal to 0. If the upper and lower limits are the same, then there is no work to do. The integral is 0. So the third property is the definite integral of f of x from a to b times c is equal to c times the definite integral of f of x from a to b, where c is any number. So as with its limits, derivatives, and indefinite integrals, we can factor out a constant. So for the fourth property, definite integral of f of x plus or minus the g of x from a to b is equal to the definite integral of f of x from a to b plus or minus to the definite integral of g of x from a to b. We can break up the definite integrals across a sum or difference. So for the fifth property, the definite integral of f of x from a to b is equal to the definite integral of f of x from a to c plus the definite integral of f of x from c to b, where c is any number. This property is more important than we might realize at first. One of the main issues of this property is to tell us how we can integrate a function over the adjacent intervals a and c and b. Note, however, that c doesn't need to be between a and b. So for the last property, the definite integral of f of x from a to b is equal to the definite integral of f of t from a to b. The point of this property is to notice that as long as the function and limits are the same, the variable of integration that we can use in the definite integral won't affect the answer. These properties enable us to simplify and manipulate definite integrals, making them easier to evaluate and apply in various contexts. Now let's try some examples and apply these properties. Consider this first example, the definite integral of f of x, which is 3x squared plus 2x minus 1. We'll apply properties 4 and 6 to solve this integral. Property 4 states that we can break up definite integrals across a sum or difference. So, we can rewrite the integral as the sum of three separate integrals like this. Next, property 6 states that the variable of integration doesn't affect the answer as long as the function and limits are the same. So, we can rewrite the integrals with different values like this. Now, let's solve each integrals. Now, we add up these results. So, the value of the original definite integral is 10.
Now for our second example, we have this sample problem. The definite integral from 1 to 3 of the function 2x plus 1 with respect to x. Here, we learned earlier the 6 main properties of definite integrals. For this part, we'll also use the fourth rule, which is the linearity property, which allows us to split the integral of a sum of difference into the sum of difference of integrals multiplied by constants. Then, with our individual functions, we can now rewrite or change the variable for simplicity purposes. After this, we can now use the main formula, which is the definite integral from a to b of the function f of x with respect to x is equal to the antiderivative f evaluated at b minus the antiderivative f evaluated at a. Here, we evaluate the upper and lower bounds. Then we have our answer, which is 10. As you can see, this is the typical standard workflow for every definite integral problems. Hello math enthusiasts, Justin here, and now we are going to talk about the fundamental theorem of calculus in the context of defining integrals. The fundamental theorem of calculus is the theorem that links the concept of differentiating a function, like calculating its slope or rate of change at each time, with the concept of integrating a function. In simple terms, the fundamental theorem of calculus states that the definite integral of a function f of x can be evaluated by finding its antiderivative and subtracting its values at the upper or lower limits on integration. The FTC has two parts, referred as the first and second fundamental theorem of calculus. To make things easier, the first part deals with indefinite integrals, and the second one, you guessed it, relates to the definite integrals. We will mainly focus on the second part of the FTC since we are talking about the definite integrals. So the second part of the FTC states that if the function f of x is continuous on the closed interval from a to b and f of x is any antiderivative of f of x, then the definite integral of f of x from a to b is equal to the difference between f of b and f of a. Obtaining the antiderivative of a function's derivative allows us to calculate the exact area under the corresponding curve between 2 points. So, what's the difference between the definite integrals with and without the use of FTC? Let's move on to the examples. Here, we have the same example used by Carlo earlier, which is the definite integral of f of x, which is 3x squared plus 2x minus 1 from 0 to 2. Here, we simply find the antiderivative of the function. Taking account the example earlier by Carlo, we can say that the antiderivative of the function is x cubed plus x squared minus x plus c. Here, c is the constant of integration since the constants in derivatives are diminished into zeros. Then, using our formula, we simply evaluate the upper and lower limits and add, giving us a total value of 10.
So for the next example, using the fundamental theorem of calculus, the definite integral of 2x plus 1 from 1 to 3. And let's use this equation. And as what Mark said earlier, an antiderivative of a function is any function or f of x such that f of prime x is equal to f of x. So for the function 2x plus 1, an antiderivative could be f of x is equal to x squared plus x. We can easily verify this by taking the derivative, which is this. Now, we apply the fundamental theorem of calculus. As we derive the answer using this, we can say that the value of the definite integral of this problem is 10.
Notice how similar it is to the definite integrals without using the FTC. But here are things to consider that can help us to interchangeably use both of them at our advantage. Definite integrals with FTC is used when finding the antiderivative is straightforward or where the function is already given as an antiderivative. And without FTC, if it can be applied directly to evaluate integrals without explicitly finding antiderivatives. But the best approach depends on the specific integrals and your familiarity with integration techniques and properties. That's it for us, math enthusiasts. Happy learning!